Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and we're going to be looking at some topical questions for paper 1 on the topic of current of electricity, or simply electricity as it's now known, for Cambridge A-Level Physics 9702. And as always, these questions come from the Papa Cambridge topical questions. I'll leave a link to these questions in the description below, but if you go to the Papa Cambridge website, you can find topical questions for all of the topics, for all papers, and it's very useful if you're studying topic by topic. So if you're studying the topic of electricity and you want to look at some specifically paper 1 questions on that topic, then you can use these questions as a gauge of, one, how well you understand the content, but how ready you are to tackle questions on paper 1, which is multiple choice. And in today's video, we're going to be looking at questions 1080 to 1090. So I'll try to do as many of these for as many topics as possible before your exam, and we'll see how far we can get. The first question here is 1080. It's from the March 2020 exam. Again, 9702 is the subject code for CAIE A-Level Physics. It's from question paper 1, variant 2, and it's question 32 from that paper. We are told that electrons move in a vacuum from one metal plate to another metal plate, and as a result of this, there's an electric current of 48 microamperes between the two plates. And we want to know how many electrons are emitted by the first plate in a time of 50 minutes. So we have to here look at the relationship between current and charge, because charge will tell us how many electrons are moving. Now, we know that current, by definition, is the charge flowing past a certain point per unit time, Q over T. So I current is Q divided by T, which means the total amount of charge passing a certain point per unit time is the current multiplied by the time, or the charge passing a point in a circuit in a time T is Q, and that's I times T. And we also know that the number of electrons, we'll call it N. We're not really going to confuse the number density here. We'll call it N. The number of electrons that will pass that point is the total charge passing that point divided by the charge of a single electron. That will give us the total number. And so this becomes I times T by the elementary unit of charge E, which is the charge on an electron, since electrons are the charge carriers. And that's 1.6 times 10 to the minus 19 coulombs. So the current here, I, is 48 microamperes. That's 48 times 10 to the minus 6, multiplied by the time. Now the time we're considering is 5 minutes. Now we can say 5 times 60, or you can simply say 300. I mean, you could do that calculation in your head. Sometimes I make mistakes on those, so I'll simply say 5 times 60 and let my calculator help me with the rest. And then I divide that by the charge on an electron, 1.6 times 10 to the minus 19 coulombs. And I get the number of electrons passing through that point in 5 minutes to be 9 times 10 to the power 16. And that corresponds with option D. So for a question like this, find the charge and then divide the charge by the charge of a single electron, and you'll know how many electrons are passing that point. So you relate the charge to the current, then relate the number of electrons to the charge, and then you can find the number of electrons in any given time T. Now the next question is 1081. It's on the summer 2020 exam. It's question paper 1, variant 1, and it's question 33 from the paper. We're given a simple circuit where the current shown is 3.2 milliamperes, and we want to know the direction of flow and the rate of flow of electrons through the resistor R. Okay, the number of electrons per unit time flowing through the resistor. So quite a tricky one. Now, I want to know the direction of electrons. They didn't ask me for the direction of current, because we know conventional current flows from positive to negative. But they didn't say conventional current, they said specifically direction of electron flow. Direction of flow and the rate of flow of electrons. And let me write the word electrons so we have it in front of us. But electrons flow from negative to positive. And so if I look at the directions in the figure, the flow of electrons, which I'm drawing here, is going to be from y to x. Remember, this is not current. They didn't ask us for current because if they did say current, we'd have to assume it conventional current, which would be in the opposite direction. So negative to positive means y to x. So immediately we can eliminate options A and B, but we can't decide whether it's going to be C or D until we find the rate of flow. So we left with a 50-50. I suppose you could do an eeny, meeny, miny, mo, but I wouldn't suggest that. Next, I want to find the rate of flow. How many electrons are passing through a point in the resistor? Let's assume the resistor is just a single point in the circuit. How many electrons are flowing through the resistor every second? And the rate of flow is the number of electrons per unit time, which is, remember we said the number of electrons is the total charge flowing through that point divided by the charge of a single electron, and then that multiplied by T, so Q over ET. But also remember that the charge is the current times the time, so I times T divided by E times T. Wait a minute, that simply becomes I over E, current over the charge on a single electron. And what I get here is the current is 3.2 milliamperes, which is 3.2 times 10 to the minus 3 amperes divided by the charge on a single electron, 1.6 times 10 to the minus 19 coulombs, which is 2 times 10 to the power 16 electrons per second. And so this corresponds with option C. So I need to find the direction of flow, which eliminates two answers, but then I'm left with another two. And I have to calculate the rate of flow in order to figure out the number of electrons passing through the resistor per unit time. But actually, I don't really, because a current of 3.2 milliamperes is a relatively high-ish current. It's not an extremely low current. It's not a current that is very high, but it's high enough. And so I wouldn't expect there to be 5.1 times 10 to the minus 22 electrons moving through the resistor every second. That's a very small number. That's less than 1 electron every second, which doesn't make sense. So you could have just guessed. You could have, after figuring out the direction of flow, by logic assumed that the number of electrons passing through the resistor would be a very high number. Electrons are tiny, they move easily, and so it should be C logically. You didn't really have to do all of this calculation like I have. Remember, in paper 1, again, it's all about saving time. You want to answer this paper as quickly as possible because 40 questions for an hour, 15 minutes is quite tight. Yes, all the questions rather won't necessarily have calculations in them, but yeah, wherever you can save time, do so. The next question is 1082. It's from the summer 2020 exam. Summer is May, June 2020. From question paper 1, variant 2, and question 33 from that paper. We are told that the number density of free electrons in copper is 8 times 10 to the power 28 per cubic meter. A copper wire has diameter 0.42 millimeters, and we want to know the average drift speed of free electrons in the wire if the current is 0.57 amperes. Now, the first thing you do when you see number density and diameters and drift speed is to write down the equation I is A N V Q. I is the current in a wire, A is the cross-sectional area of the wire, N is the number density of charge carriers, which in this case is electrons, and that's specific to the material of the wire, not to the size of the wire. V is the drift speed, and Q is the charge of the charge carriers, which in this case again is the charge of 1 electron. And so if I want the average drift speed, I can rearrange this equation. V is I over A N Q, but I don't have the area. What I do have is the diameter, and I know the area is going to be pi r squared. We generally assume that wires are cylindrical in shape. So the cross-sectional area of a cylinder, so this is my wire. I'm exaggerating the size, it's obviously going to be very, very tiny, but the wire will have cross-sectional areas, well, rather radius r and cross-sectional area a, and if I double that radius, I get the diameter. And so pi r squared, since they don't have the radius, I can just write this again as 1 over 4 pi d squared. Now that shouldn't be surprising mathematics for you. And so if I rearrange this equation to remove the area and replace it by the diameter, I get, again, this is a lot of mathematics. You don't need to do all the arithmetic or the algebra before the arithmetic. You could simply calculate the area and then put that value in. But if you know me, I like to rearrange the equation to reduce carrying big numbers through the calculation. So that's 4I over pi d squared n times q. And all of these values are known. I can put them in. That's 4 times the current. And the current is 0.57 amperes divided by pi times the diameter squared, 0.42 millimeters. So I have to multiply 0.42 by 10 to the minus 3 to get meters. And I square that, don't forget to square that number, multiplied by the number density in copper of charge carriers, or of electrons in this case, 8 times 10 to the power 28 per cubic meter, so that unit is fine. And the charge on the charge carriers is the charge of an electron, 1.6 times 10 to the minus 19 coulombs. If I do this calculation, I get the average drift speed to be 3.2 times 10 to the power minus 4 meters per second. And this corresponds to option D. So whenever you see a question that asks you about number density or diameters, average drift speeds, cross-sectional area of wires, etc., immediately you can write this equation down and figure out how to play with this equation in order to solve for whatever you need to solve for. Because if you see these kinds of things, more than likely you're going to be required to use this equation. So that was a nice question where you had to rearrange, solve for the drift speed, but also write the area in terms of diameter or in terms of radius or whatever you're comfortable with. Okay, the next question is 1083. It's from the summer 2020 exam. It's question paper 1, variant 3, and it's question 33 from that paper. Okay, it says the unit of electric charge is the coulomb. What is meant by 1 coulomb? Okay, again, this will probably not need you to use a lot of your time. You can read the possible answers and get your choice in a matter of seconds, but we'll do it as you've learned the definitions of a coulomb. Now, if I say that charge is equal to current times time, that means the coulomb, which is the unit of measurement of charge, is equivalent to the ampere times the second. But what this means is that 1 coulomb is equal to 1 ampere times 1 second. Again, by definition of current, you can see what this answer is going to be. But what this means is that if I have a coulomb of charge, that means a current of 1 ampere passes a point every second. Or current of 1 ampere is flowing through a point, and in 1 second I have a coulomb of charge passing through that point. So 1 coulomb is the charge passing a point in 1 second where the current is measured by an ammeter to be 1 ampere. And so that's option C. Again, that's by definition. That should not be something that's going to give you nightmares, because that's by what we define an ampere to be, and hence what we've defined a coulomb to be. So how those two are related. The next question is 1084. It's from the summer 2020 exam. It's question paper 1, variant 3, and it's question 34 from that paper. We have 2 copper wires joined together to carry a current as shown. Wire P has diameter D and wire Q has diameter 2D. We want to know the ratio of the average drift speed of the free electrons in P to that in Q. Now again, when they say drift speed, you go to your favorite equation, I is equal to ANVQ. But strange, I want the ratio of drift speeds. But what about all the other quantities? I'm not given anything besides the diameter. So you can tell probably that those things are going to cancel off. We know that drift speed, again I'm doing some rearranging, is I divided by ANQ. So if I want the drift speed of the electrons in P over the drift speed in electrons of Q, which is what the question is asking me for, then it's simply that ratio. It's I, it's the current divided by the area, the number density, and the charge for wire P divided by the current in Q divided by the area, the number density, and the charge of the charge carriers in Q. Now, the metal is the same. So N is the same for both. NP is equal to NQ since we have the same metal. If I was changing metals, then the number density would change. So the number of charge carriers per unit volume will remain the same. We're removing the volume from that expression. And the current is remaining the same. The current is not changing through the two wires. The current will be the same. The amount of charge passing our point per unit time will be the same. The charge may be split into a wider wire, but there will still be the same amount of charge passing every point per second. Obviously, the charge Q on the charge carrier is that of an electron, so they'll also be the same. But the cross-section area is changing. And so the only thing that changes is that this becomes the area of Q over the area of P, because only the area is changing of the wires, whereas everything else remains the same. And like I said before, area is pi r squared, or 1 over 4 pi d squared. Doesn't really matter what the 1 over 4 and pi tells us, because they will cancel as well. Those are constants. And so what this means is that I have the diameter of Q squared divided by the diameter of P squared. And they already told us, P has a diameter D, Q has a diameter 2D. So this is 2D squared over D squared, or 2D over D, all squared, which the D's cancel, leaves me with 4. So I double the diameter and I quarter the drift speed. So if the diameter is halved, then the drift speed increases by a factor of 4. And this corresponds with option D. So again, these ratio type problems are very common. It's always good to learn how to deal with ratios. Knowing what remains constant when there are two scenarios like the case we have here, and what changes will help you solve these problems. Knowing the current remains the same. Whatever current goes in must be the current that comes out. Yes, the wire is wider, but the speed of the electrons will ensure that the current remains the same. The amount of charge passing a point per unit time remains the same. And so that remains the same, meaning everything else cancels besides the areas, and the areas can be related to the diameters, and so we get the ratio 4. So you have to know a few things here. Know I is equal to A and VQ. Know that diameter is related to area by D squared, and that'll help you solve these kinds of problems. The next question is 1085. It's from the March 2019 exam. It's question paper 1, variant 2, and question 32 from the paper. We're told that the electric current in a wire may be calculated using the equation I is equal to A and VQ. At least they give us the equation this time. We want to know which statement is not correct. Okay. N is the number of charge carriers per unit volume, and A is the number of charge carriers per unit length. Q is the charge of each carrier. V is the velocity of each charge carrier. Okay, let's write this equation down and let's test all of these variables, all these symbols. What do we know from the definition or from the statement of this equation is that A is the cross-sectional area, and it's measured in meters squared, just like we always measure area. N is the number density. I'm not going to say number density of charge carriers because I'm lazy. I'm simply going to say number density. How many electrons do I have per cubic meter? So the unit of measurement is per cubic meter. V is what we call the drift speed. There's no direction associated with V. It's just the average speed of the electrons that are moving through the wire. I don't account for the direction, because if I accounted for the direction, with everything else being scalar, that means current would be a vector as well. And we know current is a scalar quantity. Charge of charge carriers, I'm just going to say charge again, charge of electron or elementary charge or charge carrier, whatever. But what about NA? One of the options of NA. Well, if I take per cubic meter and I multiply it by square meters, what do I get? I get per meter. And so that gives me the number of charge carriers per unit length. So that actually does check out. It actually is the number of charge carriers per unit length. So the only one that doesn't stand out here is the last one, D, which says V is the velocity of each charge carrier. If V was a velocity, I, the current, would be a velocity as well. And that's not going to stand because everything else is scalar. I is scalar. V cannot be a velocity. V is actually the drift speed. And so what is standing out here is option D. It's not correct to say that V is the velocity of charge carriers. It is the drift speed of the charge carriers. Okay, the next question is 1086. It's from the summer 19 exam, question paper 1, variant 2, and question 33 from that paper. We have a length of wire connected to a circuit. The area of the cross section of the wire changes from A at R to half A at S, and there's a constant current in the wire. Charge Q passes R in a time t. What is the charge passing point S in the same time t? So S has half the area that R does. And we want to know how much of charge is passing through S if Q is passing through R. Okay, what I know that current is charge per unit time. And I know that the current is constant. So the current is not changing between R and S. So simply I can say that the current at R is equal to the current at S. But the same time elapses for us to count the charge moving past R as it does through S. So the time that we're measuring for the charge that is flowing past R is the same time that we measure for charge flowing through S. So wait a minute, what that means is I have the same current and the same time. That means the amount of charge flowing through R is equal to the amount of charge flowing through S, which is equal to simply Q, option B. Okay, so this question, I didn't really have to think about drift velocities and so on, but what will happen here is even though the area becomes smaller, the electrons will speed up to make sure that as many of them pass a point in a unit time as they would at R. And so the speed increase ensures that the current remains the same. And so even if we change the thickness of the wire, the current in the wire remains the same. Sort of like water through a pipe. If we decrease the area of the cross-sectional area of the pipe, the water will increase its speed to ensure that the flow rate remains constant. So the charge will simply be Q. The next question is 1087. It's from the winter 2019 exam. That's October-November 2019. It's question paper 1, variant 1, and question 30 from the paper. We have a metal plate of uniform thickness is being connected to a cell as shown, and we're given a circuit diagram of the plate viewed from above. Electrons move clockwise around the circuit, and we want to know which of the statements about the metal plate is correct. The average drift speed of the conduction electrons decreases as they move from right to left through the plate. The average drift speed of the conduction electrons increases as they move from right to left. The number density of the conduction electrons decreases from right to left. Or D, the number density of the conduction electrons increases from right to left. What did we say about number density N? Number density depends on the metal. It depends on the substance to which the current is being conducted. I have the same metal throughout. This entire metal plate is made from one metal, so N must be constant, meaning we can immediately eliminate options C and D. So it has to be option A or option B. Now, I know that the current flowing through the plate, I, is ANVQ. And the drift speed, why am I rearranging from the drift speed? Because the two statements here are talking about drift speed. The drift speed is equal to the current, which is constant, divided by the area times the number density times the charge. Now what is happening as I move from right to left, because both options say right to left, as I move from right to left, the area is decreasing. So if I look at this expression that I have here, the area is in the denominator on the right-hand side. So if the area decreases, this means that the drift speed must increase. Everything else is remaining constant. So for the area to decrease, the drift speed must increase. And that will make sure, again, like I said before, that the current remains constant. As long as I have the same potential difference, I will keep the current constant. And so this corresponds to option B. The average drift speed of the conduction electrons increases as they move from right to left, where area goes from big to small, meaning area decreases, and the drift speed increases. So again, another interesting question. These kinds of questions are very common, and I would suggest, whether you're preparing for paper 1 or paper 2, be able to work with these questions where they ask you about the I is equal to A and VQ scenario. If you can handle that, you can handle most questions on this topic. I think this is the most difficult thing, one of the most difficult things, at least for me, in this topic. The next question is 1088, that's 1088. It's from the winter 2019 exam. It's question paper 1, variant 1, and it's question 31 from that paper. Now on the diagram, we are shown the direction of current in a metal block, and the charge carriers enter the block through the face PQRS and leave the block through the opposite face. The number density of charge carriers is N, each charge carrier has a charge E, and the drift speed, or the average drift speed of the charge carriers is V. And we want to know which expression gives the current in the block. Okay, so let me just redraw the face that we really cared about, PQRS. In fact, I should label it as well, just so there's no ambiguity. So this is the face through which the current is passing. Essentially, the cross-sectional area is the area of the face through which the current is passing perpendicular, which is PQRS. And so I have my current flowing perpendicular to this area. So the cross-sectional area through which the current is passing is simply X times Y. I don't really have to care about the areas of the other sides, because the current's only passing through this face. But wait, the current, which the question asked me for, they asked me for the expression of the current, is equal to A N V Q. But A is equal to X times Y. That means the current is the area XY multiplied by the number density of charge carriers multiplied by the charge of each charge carrier, which is E, times the number density, which they told us is N, times the drift speed, which they told us is V, and times the area XY. So I is equal to ENVXY. I wrote the XY at the end because that matches what I see in the solution. So that corresponds with option B. So maybe trying to throw you off with the different sides of the figure, but simply cross-sectional area, not total surface area of the surface. So just be very careful. This is something, again, you will see when you do A-level physics and you study magnetic fields and you talk about things like the Hall effect. But the cross-sectional area is A, and we aren't talking about the total surface area. So I think that's where they were trying to maybe get you to falter. But we didn't, and we got this correct. That's option B, ENVXY. The next question is 1088, 1088 from the winter 2019 exam. It's question paper 1, variant 2, and it's question 31 from the paper. And we are told that there's a current of 5 amperes in a wire, and the drift speed of the conduction electrons is 7.4 times 10 to the minus 4 meters per second. And we want to know which row gives a possible cross-sectional area and number of conduction electrons per unit volume for this wire. Okay, so this is a bit of a different question. We have two unknowns, and we only have one set of data. So we're going to be doing a little bit of guess and check here. But when I have all these quantities, I know I have to turn to the equation I is equal to A N V Q. Now what I want is a possible cross-sectional area and a possible number density of electrons. So I want A and N separately. So I'm going to separate AN. I'm going to write AN as I over VQ. Basically, I'm writing the unknown things on the right-hand side, and I'm putting the known things, or rather the unknown on the left-hand side and the known things on the right-hand side. And let's put the values in, shall we? So the current is 5 amperes, that's given. So that's 5. Again, I don't need to write the units if everything is in SI units. It's 5 divided by 7.4 times 10 to the minus 4. And the charge carriers of an electron, the charge carriers are electrons, and they have a charge of 1.6 times 10 to the minus 19 coulombs. And this gives me 4.2 times 10 to the power 22. Now what is left for me to do is to try and figure out which combination of area and number density, which row, if I multiply these two numbers together, which one of them gives me 4.2 times 10 to the power 22. And it turns out, I'm not going to do all of them, but you can test this out for yourself. It turns out to be 7.2 times 10 to the minus 7 square meters for the cross-sectional area. It should be very small. And the number density of electrons should be 5.9 times 10 to the power 28 per cubic meter. And this corresponds with option B. So you had to do a little bit of guess and check there, but it shouldn't take you too long to determine which values, because you simply need to multiply them together. So you could do that in your calculator very rapidly and see which gives you 4.2 times 10 to the 22. So like always, when you see questions that ask you for drift speed and cross-sectional area, immediately go to the equation I is A and VQ. The last question is 1090. It's from the winter 2019 exam. And this is the last question we'll do in this video. It's from question paper 1 variant 3, and it's question 33 from the paper. A metal electric conductor has a resistance of 5.6 kilo ohms and a potential difference of 9 volts is applied across its ends. We want to know how many electrons pass a point in the conductor in 1 minute. Okay, so it might just be worth me drawing a simple diagram of what's happening. So here's my conductor, whatever it is. I'm going to draw it as a resistor just because we have a resistance value. I'm going to say the resistor has 5.6 kilo ohms of resistance, and we attach a voltmeter across the resistor, and we find that the potential difference is 9 volts. We want to find how many electrons pass a single point in the conductor in a minute. And so I'm going to apply Ohm's law here. I is equal to V over R. Because I've got voltage and I've got resistance, but I'm also expected to answer questions on number of electrons, which requires me to know current. Now, by definition, current is charge per unit time. So charge per unit time is V over R, Q over T. But we also know that the number of electrons passing a point is the total charge passing that point divided by the charge of a single electron. So what I can write is this becomes Ne divided by T equal to V over R. And what I actually want in this question is the number of electrons, how many of electrons are passing the conductor in a minute. So I want N over T. Number per unit time, number per second. And this is equal to V over ER. And this is the potential difference. Now I have all those values that I need on the right-hand side. So this is the potential difference of 9 volts divided by the charge, the elementary charge, 1.6 times 10 to the minus 19 coulombs. The resistance is 5,600 ohms, it's 5.6 kilo ohms. And what I get is 1 times 10 to the power 16. So I happily can go and choose the answer 1.10 to the power 1 times 10 to the power 16, which is option D. But I have to be very careful. What I calculated was the number of electrons passing through a point in the conductor every second, because we're measuring time in seconds here. It's SI units. So that's per second, and I have to multiply this by 60 because there's 60 seconds per minute. And then I can say goodbye per second times the second disappears, and I'm left with, if I multiply 1 by 60 times 10 to the power 16, I get 6 times 10 to the power 17 passing through a point every minute. So I had to be very careful there. The first answer that I was glaring me in the eye was not the correct one, and so I have to make sure I overcome that confirmation bias and I actually test and make sure that I'm calculating this for a minute. So I get 6 times 10 to the 17 every minute, which corresponds to option C. So these questions were quite interesting. They were not the easiest, but not as difficult as what we will see in DC circuits, which actually require working knowledge of circuits and how, when these quantities like current, etc., change, other quantities change as well in response. And so it's very important to understand the fundamentals. If you don't understand the fundamentals in electricity, you cannot move forward to the topic of DC circuits. So I hope this video and these questions were helpful. If they were, please leave a like, comment on this video. If you haven't subscribed to the channel, please do so now. But from me, Mr. K, that's all for now. I'll see you again next time on Everything is Relative.